recall that when we defined a vector line integral, let's say, for vector line integrals, you may remember that orientation mattered. Whereas with scalar line integrals and scalar surface integrals, orientation does not matter. However, for vector line integrals and what we will see is that for vector surface integrals, orientation does matter. And we had the orientation, we had oriented curves, right? Where the convention was positively oriented is counterclockwise and negative is clockwise, right? We had, so if you have some curve, maybe it has self-intersections even. A positive orientation was to define this so that it's traveling counterclockwise, right? And negative would be, you could define the same curve, and if you give it a clockwise orientation, by convention we would say this is negative. Now, these curves, what an orientation is it's a choice of, you pick a direction, right? So at each point, you have a vector pointing in either direction. So what is the tangent space of a given point along this curve? The tangent space is a copy of the real line, right? And an orientation is a choice of a vector. You have two choices, left or right here, right? Well, quote unquote, left or right. That's kind of ambiguous if you're like vertical or something. But at each point, the orientation is a choice of direction in the tangent space. And here, we can orient surfaces as well. So let's look at the orientation of a surface. Now, if we think about like a sphere, maybe, and I said that to choose orientation, what you do is you look at the tangent space at a point, and then you're tasked with making a choice. You can choose to orient it clockwise or counterclockwise for a curve. Well, now what's the tangent space of a surface? Well, now the tangent space of a surface is R2, right? Here, the tangent space at a given point was R. Well, now the tangent space is R2. And now you have a choice of two vectors here, right? If we label these E1 and E2, you could see there's two choices, is to have E1 go first and then E2, or you could have E2 go first and then E1, right? These are different. You cannot continuously move vectors around to get from E1 to E2, this E1, E2 to E2, E1, right? You can't get from one to the other. However, any other collection of vectors, of two vectors, like however you want, right? That can be expressed as like a rotation of these vectors. And so you could have like E1, E2, E1, E2. And you see here, this is just a rotation of this. And in fact, this is then a rotation of E1, E2, right? And you see there's no way to get from here to here. And so that means we still have a choice, but now it's two vectors since our tangent space is R2. And we can boil this down to a choice of one vector if we think about taking the cross product. If we were to look at, so say on a surface, right? So say there's a surface doing something like this here, and then it has tangent space R2. So here's our surface S down here, maybe doing something like this. And then we're looking at like the tangent space at a point at somewhere like at the top of this hill, maybe not exactly the top, but somewhere at the top, right? And if we chose E1, E2, where E1 comes first, then if we took E1 cross E2, we would get some vector E3, which is perpendicular to both E1 and E2. This is actually a normal vector. E1 and E2 are both tangent to the surface. So something perpendicular to something tangent, or something perpendicular to tangent space is perpendicular space, right? Because you take a 90 from being tangent, that's what it means to be orthogonal or perpendicular. And so that means taking the cross product is a normal vector. And if we were to equip this with the opposite orientation, maybe we decided to take E2, E1, well then E2 cross E1 would be negative, right? And so this would actually be going down, like inward, in towards the surface. So we have two vectors in and negative in. And so we can define an orientation of a surface not by a choice of two vectors in the tangent space, but by a choice of a normal vector. So let's give a definition here. An orientation of a surface S is a choice. It's not canonical, right? It's a choice of a normal vector to S. And so, for example, we usually think about these choices, the two choices, as inward and outward. So one orientation of the sphere, the outward normal vector, would be like a porcupine, like a hairy ball. Something like this, right? Where you're picking normal vectors. So some of these vectors don't look quite normal. They just look like they're going straight out, right? But like normal, meaning it's perpendicular to the surface or orthogonal to the surface, right? So that's one choice of orientation. You have outward or you have inward. Where you equip the sphere with the opposite orientation and all the normal vectors are pointing inside the sphere. Something like this. And we get a well-defined notion of orientation of a surface now because we can choose a normal vector to orient our surface. And in fact, remember, I said these normal vectors were coming from vectors in the tangent space, right? This is the tangent space of the surface S at a point. Well, there are two very, very important vectors that live in the tangent space to a surface, and that is the partial derivatives. So we could let E1 be the tangent vector in the u direction, where S is parameterized by R of uv. Let's say S equals like R of uv here. That's horrible notation, right? But how about S colon? Say S is the surface R of uv. We could let E1 be the tangent vector that's indicating change in the u direction, and E2 being the tangent vector that's indicating change in the v direction, right? And so we're looking at like you have some surface like this, then you have a tangent space, and then we have TU and TV. And we can construct our normal vectors purely from this TU and TV. And so the outward, well, so it won't always be the outward depending on the function and depending on the surface. So let's say we can think about the unit normal vector in being defined as TU cross TV divided by its magnitude, right? And then so the other choice is negative n, right? Which is just negative this value, which is TV cross TU over the magnitude of TV cross TU. Okay, and so when we're defining orientations of surfaces and using this to define vector surface integrals, we will come back to this definition of unit normal vectors, right? This is a unit normal vector field along the surface S. These are unit normal vectors. And so are these, negative n, that's just in, take a pi rotation. Okay, I do want to quickly make a remark, is that there exist non-orientable spaces. I think non-orientable spaces are very interesting to examine. The first and maybe most famous example of a non-orientable surface is a Mobius strip. So example, a Mobius strip. So a Mobius strip, if you don't know, is you take, and you can do this with a sheet of paper. Take a strip of paper, like cut it pretty thin, and I can label my vertices, like the four corners, A, B, C, and D. And to construct a Mobius strip from paper, you hold one end fixed. So we'll keep this A, B end fixed, and then you twist the other end. So you have like D, C. So you twisted your paper like this. And now you kind of bring, after you perform this twist, you wrap this around and tape it together. And so the side AB becomes taped to the side DC. And so what we get is that the points, we have points A and D are now the same point, and B and C are now the same point. But when we wrap this around, we get like a circle here, right? And so trying to, kind of tricky to draw sometimes. Like what starts at the bottom as you go around comes up to be the top here, right? And then this comes around. And let me indicate that this is behind. So we have AD, and then this comes over, down like this, and then this wraps back around like this. And you get a sheet of paper, you get like a loop with a twist in it. This is not orientable. If you imagine, if I take a vector that is outward at a given point, and I start to travel around this Mobius strip, and so now my outward pointing normal vector, so I've chosen an orientation of this Mobius strip, right? I've chosen my vector to be outward normal, and I'm going to travel around this Mobius strip like this. And as I go around, once I hit this twist, here. Once I hit this twist, the vector it becomes an inward normal vector, right? Once I go along that twist, you can think about, like in this picture, the vector kind of goes under and then back up. But when it comes back up, it's pointing on the inside. And so I hit this point, once I make one full circle, well, when I come back to this spot, now my supposedly outward normal vector is now an inward normal vector, which means you cannot, this orientation is not well defined, right? Because what was supposed to be an outward normal vector at the exact same point is now an inward normal vector. Means this is non-orientable. This is a non-orientable surface. And so that means we're only going to be defining vector surface integrals over orientable surfaces. I do want to say one more example that is very, very interesting of a non-orientable surface is, I would definitely take a look. I would just Google or Wikipedia non-orientable surfaces. And take a look. I think it's very cool. Another example that's very cool is the real projective plane. The notation for this, so usually you just say, like a Mobius strip, this is the surface M, right? The real projective plane, the notation is RP2. And I would definitely suggest Googling RP2 and taking a look at some of the properties of this space. It's a very interesting space. Here's how you define it. You take a sphere, S. There's many different ways to construct or define RP2. I find this one to be the most geometrically intuitive, so I'm going to describe it. So let's say you have a point X on your sphere, right? You have this point X. You draw a line through this point and the origin. So you take a line that kind of intersects, you see it's going to intersect the sphere twice, right? It intersects the sphere at X, and then it intersects the sphere at some other point. So we have, we'll call this point negative X. Okay, and so now we have 2 points. These are called antipodal points. X and negative X are antipodal, right? Meaning they're on the same line that passes through the origin, but they're on opposite ends of the globe, right? And so these are antipodal points here. And RP2 is generated by taking the sphere. So we will indicate the sphere. Let's call this surface, we'll say it's S2. RP2 is given by taking S2, but setting X equal to negative X, or I would say identifying. Say this is, RP2 is the sphere where we identify X and negative X as the same point. And so this is really hard to picture, and it's even harder to draw. Wikipedia might have like an artist's rendition of what RP2 would actually look like. But so if you can imagine, you take all these lines through the sphere, and for every pair of opposite points, you say, okay, well, those are actually like wrapped around to be the same point, right? You kind of take the surface and you stretch it until those become one point. And then you do that for every pair of opposite points on the sphere. And then you get the real projective plane. there's a lot of interesting proofs about why this space is not orientable. And so if you're interested in this kind of stuff, I would recommend giving it a look. It's a step up in difficulty to the Mobius strip. It's pretty intense to kind of fully explore RP2 and its properties. But it's very interesting, and I would definitely suggest taking a look at RP2 to see if you can get a better idea of picturing what this space is, and then also why it's not orientable. Okay, so now that we've gotten all of this about orientable and non-orientable surfaces out of the way, we're only going to talk about orientable surfaces. And let's now define, we're ready to define the vector surface integral. Okay, so first let's understand what the vector surface integral is doing. So here's the idea. The vector surface integral calculates the flux. We learned how to calculate flux when we discussed, like I believe it was like line integrals and stuff like this. Yeah, like vector line integrals. It's calculating the flux, but now instead of along a line, it's through like a membrane, right? Like a two-dimensional, like permeable membrane or something like this. So the idea is that a vector surface integral calculates the flux of a vector field along surface S, and then let's say parameterized by, we'll just go R of UV here. Okay. So now that we have an idea of what this is, let's see how to actually construct it. So we have some surface S, like this, say. And then we have a vector field kind of flowing through here, F, right? And so this is a surface S given by R of UV with parameter domain D. We also have a normal vector field N here. And so what I've drawn is more representative of the normal vector field. So let's say N is the normal vector field in the color black, and then we'll have F in green, right? And it could be doing something different per se. Right? And we want to calculate the flux through this. So we have F is a vector field, N is the, I think I want it, yeah, let's let N be unit normal vector field. Okay, and now to calculate flux, we need a few things. We need the density, right? And so when we're thinking about flux, we're thinking about the surface S as kind of like a membrane that a substance or fluid or material or whatever is passing through this membrane unobstructed. And to calculate flux, we need to know the speed at which this substance is traveling, and we need to know the density of this substance. So let's define rho of XYZ to be the density of the substance traveling, or let's say flowing, I like that word better, flowing through the surface S. And we also need the vector field v, which gives us the velocity of the substance flowing through S, right? And now, how are we going to calculate flux? Well, calculating flux is rate of flow, which is, what is a rate of flow? Well, this is mass per unit time, so mass per time per area, right? And so what this means is, well, we need something that's mass per time per area. We can calculate this by simply looking at rho times our unit normal vector, right? This unit normal vector we have a unit normal vector over this kind of grid-like S, just as we did for scalar line integrals here, or scalar vector integrals, excuse me, right? We have all these normal vectors that we can take. And we have the density here of this substance. And so to get mass per time per area is going to be rho in here, right? Because the magnitude of this normal vector is going to be the area of the parallelogram spanned by the cross product of the vectors at the base of this normal vector here. And so we get the rate of flow with rho in. And now if we look at, say, where am I? So I wish this was in blue. Remember, we broke this up into these S sub ij's, which are these little mini parallelograms, right? And then the point in the lower left corner we said was Pij. Okay. And now, what else do we need to calculate flux? We need rho v in the direction of n, right? Because we need to understand what is flowing through this surface at like a perpendicular, right? Because anything flowing through this surface, to understand flux, we need to know what this is and the direction of the normal vector n. And so we can obtain this by taking the dot product. So understanding the material flowing in the direction of n is just given by taking the dot product. And now, what do we need? Now we need the mass, right? The mass of the fluid flowing through S. And this is given by, well, it's rho v in the direction of n, but now we need to account for the area, right? And we called the area here delta Sij. So times delta Sij. This gives us the mass of the fluid flowing through one tiny little sub-rectangle or sub-parallelogram here. And now we're equipped to approximating the flux across S, putting all of this together, right? We have that the flux is approximately equal to, because the flux through this little piece here, we need to sum this up over the entire surface S, right? And this is sum I goes from 1 to m, j goes from 1 to n of rho v dot n times delta Sij. And now this was a construction via a physics example, right? But let's replace rho v with an arbitrary, so replace rho v with an arbitrary vector field, let's say F. So then the flux is approximately double sum I equals 1 to m, j equals 1 to n of, now we have just F dot n delta S I j. And this leads us to the definition for a vector surface integral. So definition of a vector surface integral. Okay, the vector surface integral of F, vector field F over surface S is, we write double integral S and we write F dot D capital S. This is our notation for a vector surface integral. This is given by the scalar vector surface integral of F dot n ds. Okay, and so we describe the vector surface integral in terms of the scalar surface integral, right? And where did this come from? Well, you can see here, this formula is exactly what we would get by taking the limit of this approximation of flux as m and n both tend to infinity. And we can see why then that the vector surface integral is calculating the flux of a vector field through a surface S. Now, let's take our knowledge of scalar surface integrals to come up with a more explicit formula to actually calculating vector surface integrals. So we have the vector surface integral F dot ds is the scalar surface integral of F dot n ds, where, remember, I said we would come back to the normal, the unit normal vector field, which is also why the choice of orientation of our surface matters, right? We have that n can be expressed as Tu cross TV over its magnitude. And so this becomes, let me give myself some more room here. This becomes the double integral, the scalar surface integral of F, and let's plug in our parameterization. R of uv dot, now what's n? N is Tu cross TV divided by the magnitude, Tu cross TV, but ds. And now, if you recall, when we learned about scalar surface integrals, let's see if I can find it. When we learned about scalar surface integrals, look at this formula here. We have that ds is equal to the magnitude of Tu cross TV times du dv. We kind of secretly learned this equality, that ds is equal to the magnitude of Tu cross TV du dv, right? And using that information to simplify our formula for calculating a vector surface integral, this becomes scalar surface integral F of R of uv times our unit normal vector Tu cross TV divided by the magnitude of Tu cross TV. Well, then we learn that ds is the magnitude of Tu cross TV du dv. And when I pass from ds to magnitude of Tu cross TV du dv, I need to pass to the parameter domain being the bounds of integration here. So this is d, where d is the bounds for u and v, right? You can see we get cancellation. That magnitude will be non-zero because we're looking at a smooth parameterization. And so this becomes the double integral over the parameter domain D of R of u of v dot product Tu cross Tv du dv. And here is our full representation now, or our most explicit version of being able to calculate a vector surface integral. And so here you can take it as a theorem, maybe, that the vector surface integral f dot ds, so let's let R of uv equal x of uv, y of uv, z of uv. Okay, and so then how we calculate a vector surface integral is the double integral over the parameter domain D. So let me say R of uv with parameter domain D is you plug in the parameterization to the vector field, and then you take the dot product with the cross product Tu cross Tv, du dv. Okay, where, remember, t sub u and t sub v are the tangent vectors that are calculated from the parameterization. So this is the vector dx, du, dy, du, dz, du, and t sub u is dx, dv, dy, dv, dz, dv. And this gives us a full construction and understanding of vector surface integrals. And we need to, again, have to know how to parameterize a surface. We have to know what our vector field is, F, right? Capital F. And then we need to be able to compute tangent vectors. And then if we can do all that, we plug it into the integral and compute. So let's finish up this lengthy 3-part lecture on surface integrals by doing an example. Let's calculate the vector surface integral SF dot ds, where F is the rotational vector field negative y x 0, and S has parameterization R of uv equals u v squared minus u and u plus v for u between 0 and 3 and v between 0 and 4. And remember, possible u and v values here, this is our parameter domain D. That's what I mean by a parameter domain, right? It's the possible u and v values that you can input. So let's calculate this. Integral S f dot ds is, using the formula, well, what do we need? So maybe before we calculate this, I tend to like to break these problems into pieces. What's the first piece we need? We need f of R of uv. So what is f of R of uv? Well, f is negative yx, and then we have the parameterization where x equals u, y equals v squared minus u, and then z equals u plus v. So let's plug this in. F of R of uv then is negative v squared minus u comma x, which is u, z remains 0. So f of R of uv is the vector field u minus v squared, u 0. And now we need, what else? We need Tu cross Tv. where these are given by the partial derivatives with respect to u and v, respectively. So let's calculate these separately and then take their cross product. Tu is the derivative of x with respect to u in the first component, which is 1, right? Because derivative of u is 1. Derivative with respect to u in the second component is -1 and then 1. And then so for TV, it's the derivatives of r, but now with respect to v. So 0, 2v, 1. Okay, and we need their cross product. So Tu cross TV is I, J, K. And then T sub U was 1, -1, 1. T sub V was 0, 2v, 1, 0, 2v, and 1. We calculate their cross product to be -1 minus 2v I hat minus 1 minus 0 j hat plus 2v minus 0 k hat. And so Tu cross TV is the vector -1 minus 2v, -1, 0. Awesome. So we have r of u, f of r of uv, and we have Tu cross TV. And we use our formula now that says the vector surface integral of f dot ds is double integral over the parameter domain D of f of r of uv times magnitude of Tu cross, or not magnitude, excuse me, it's just dot product Tu cross dv, du, dv. Well, we know what D is. U goes from 0 to 3, and V goes from 0 to 4, right? This was our parameter domain D over here. And then f of r of uv is u minus v squared u 0. So u minus v squared u 0 dot Tu cross TV, which is -1 minus 2v, -1, 0, du, dv, which is double integral. U goes from 0 to 3. V goes from 0 to 4. So it's kind of messy down there. But it's the same bounds as the integral right above it, right? And then so we have u minus v squared times -1 minus 2v, taking the dot product, and then plus u times -1 plus 0 du dv. We can simplify this a little bit. U goes from 0 to 3. V goes from 0 to 4. And what we'll get is we'll have a negative U minus 2uv plus v squared plus 2v cubed, plus v squared plus 2v cubed, and then minus u du dv. And so this becomes a double integral. U goes from 0 to 3, v goes from 0 to 4 of 2v cubed plus v squared minus 2uv minus 2u du dv. And now this integral is completely set up into a double integral that we know how to compute, and I'll leave the rest of the work for you guys to verify that the answer that you get is 340. And so here's an example of calculating a vector surface integral. And again, to calculate a vector surface integral, what you need is to parameterize your surface, plug that parameterization into the vector field, take the dot product of the cross product of the tangent vectors that you get by taking your partial derivatives of r, right? Because r is given by x, y, z. And then you have this integral to take the dot product, or you have this integral with the dot product. You take the dot product, and then you get somewhere like this, where it's just a standard double integral that we know how to calculate. And so this concludes our lecture, the 3-part lecture on surface integrals. As we wrap up the course, there are 2 main theorems that are left to discuss, namely a theorem attributed to a mathematician named Stokes, and then the divergence theorem. These are both very important theorems that bring our subject of vector calculus and multivariable calculus in a whole to a nice conclusion.